Welcome back to Sleepy Universe. Tonight, we are going on a journey, a very long, very slow, and very quiet journey through the entire history of our planet Earth. This story is not a short one. It spans an almost unimaginable length of time, over 4.5 billion years. It's a story that begins in the void of space and leads to the world outside your window. It's a story of incredible change, of patient, gradual transformation. We will move through this story slowly, step by step, fact by fact. There is no need to remember every detail. Simply let the words and the science wash over you. Let the scale of deep time quiet your mind. So, settle in. Let the day fade away. And let's begin our journey back to a time before the Earth even existed, to a time of drifting dust and silent gas. Chapter 1. The Cosmic Cradle, a gentle beginning in a violent universe. A time before planets, before the sun, before there was anything in our solar system to catch the light. We must journey back, not just in years, but in imagination, to a place of profound darkness and quiet. This is our starting point. A vast, cold, and immensely large cloud of gas and dust, drifting in the silent black between the stars. This cloud, what astronomers call a nebula, was the nursery for our entire solar system. It was not empty. It was a floating sea of elements. Mostly, it was the light gases, hydrogen and helium, the most simple and ancient elements in the universe. But mixed within this gas was something special, fine, microscopic dust. This dust was made of heavier things, grains of silicon, iron, carbon, and ice. These particles were the ashes of stars that had lived and died long before. When those ancient stars reached the end of their lives, they exploded, scattering these elements across space. Our solar system, and everything in it, including you and me, is made from this stardust. We are, quite literally, the children of long-dead stars. For millions of years, this cloud drifted, undisturbed. But in the cosmos, nothing stays still forever. The trigger for the birth of our solar system was likely a gentle nudge. Perhaps it was the shockwave from a nearby supernova, a dying star sending a ripple through the fabric of space. Or perhaps it was simply the natural, invisible tug of gravity within the cloud itself, causing a small, dense region to begin pulling everything else toward it. And so, the great collapse began. It was not a fast or violent process. It was a slow, graceful, and inevitable fall. Gently, persistently, gravity pulled every atom, every molecule, every speck of dust inward toward the center of the cloud. As this vast cloud contracted, a fundamental law of physics came into play, the conservation of angular momentum. It sounds complex, but the concept is simple. Think of an ice skater. When they spin with their arms outstretched, they spin slowly. But when they pull their arms in tight to their body, they spin much faster. The same thing happened to our cloud. It had a tiny initial bit of spin. As it shrank, that spin became faster and faster. This increasing rotation caused the cloud, which was once a roughly spherical shape, to flatten. It became a giant, spinning disk, a protoplanetary disk. Imagine a massive, swirling frisbee, billions of miles across, with a growing, dense and hot ball of material forming right at its very center. All the future planets were in that disk, waiting for their turn to form. Now, let's focus on that center. As more and more material piled in, the pressure and temperature at the core became astronomical. What was once a cold, dark cloud was now a hot, glowing object known as a protostar. This young sun did not yet shine from nuclear power. For tens of thousands of years, it glowed with the simple, intense heat of compression. The energy released from all that gas and dust smashing together under the immense force of its own gravity. Then, a critical moment arrived. The core temperature reached a staggering 15 million degrees Celsius. At this extreme heat and pressure, the atoms of hydrogen, which had been zipping around independently, were forced together with such violence that they fused. They merged to create a new, heavier element, helium. This process is nuclear fusion, and it releases a truly colossal amount of energy. With this stable, self-sustaining fusion reaction ignited, our sun truly turned on. A star was born. Its light, for the first time, flooded the nascent solar system, and the solar wind, a stream of particles flowing from the sun, began to blow away the leftover gas from the inner disk, clearing the view for the rocky planets to come. Our attention now returns to the material left in that spinning disk. The stage was now set for the next act, the building of the planets. It started once again with the smallest of things, the dust grains. These tiny particles, no larger than specks of smoke, began to float into one another. In the microgravity of the disk, they didn't bounce away. They stuck together, held by static electricity, like dust clinging to a television screen. This was the first step in a process called accretion. Slowly, over hundreds of thousands of years, these specks became pebbles. The pebbles became rocks. The rocks, in a slow, stately dance, began to collide and merge. When they collided gently, they stuck together, forming larger and larger objects. When they collided with more force, they sometimes shattered, but the pieces would eventually recombine. This was not a chaotic smash-up, but a persistent, gradual assembly. Over millennia, these rocks snowballed into mountain-sized bodies called planetesimals. These were the true building blocks of planets. The inner part of the solar system was a busy construction zone, filled with countless planetesimals orbiting the new sun. Through a process of gentle collisions and gravitational attraction, a few of these planetesimals began to grow larger than the others, dominating their orbits. These were the protoplanets, the embryos of the worlds we know today. Because the inner solar system was warm, close to the heat of the young sun, only materials with high melting points, rock and metal, could condense and survive here. This is why the four inner planets, Mercury, Venus, Earth, and Mars, are all rocky, terrestrial worlds. They were built from the dust of rock and metal. One of these protoplanets, in an orbit that would later be known as the Goldilocks zone, not too hot, not too cold, was the body that would become our Earth. But this early Earth bore no resemblance to the blue marble we know. It was a hellish world, a seething sphere of molten rock. Its surface was a global ocean of magma, constantly churned by the immense heat from within. This heat came from two main sources: the relentless bombardment of the remaining planetesimals and the energy released by the decay of radioactive elements deep inside the planet. There was no solid ground, no atmosphere. The sky was black, lit only by the brilliant new sun and the constant, silent glint of other orbiting debris. It was during this violent, final stage of planetary construction that the most significant event in Earth's early history occurred. Another large protoplanet, perhaps the size of the planet Mars, shared a similar orbit. Scientists have named this body Theia. For millions of years, the early Earth and Theia circled the Sun in a gravitational resonance, a cosmic dance where their paths slowly, inevitably, drew closer together. Their meeting was not a glancing blow. It was a direct, cataclysmic, and yet almost graceful merger. Theia did not simply strike the Earth. It plunged into it. The energy released was so immense, so far beyond human comprehension, that it did not create a crater. It vaporized both worlds. The Earth and Theia ceased to be two distinct bodies, and, for a brief time, became a single incandescent torus of vaporized rock and metal, a donut of destruction spinning wildly where a planet had once been. From this chaos, a new order began to form. The force of the impact sprayed an enormous amount of material, primarily from the rocky mantles of both worlds, into a wide orbit around the still coalescing Earth. This material formed a ring of molten rock around our planet, a brilliant, glowing arch in the sky, far more spectacular than the rings of Saturn. And then gravity began its work once more. The particles within this ring of fire started to attract one another, clumping together. Within a surprisingly short time, perhaps only a few hundred years, this dispersed material was gathered up, accreted into a single, larger body. From the fiery debris of a cosmic collision, our moon was born. This origin story, the giant impact hypothesis, explains so much of what we see today. The moon has a much smaller iron core than Earth because it formed primarily from the rocky mantles of both worlds. The composition of moon rocks, brought back by astronauts, is strikingly similar to the composition of Earth's mantle. It is a piece of our own planet, orbiting us as a constant reminder of our violent birth. So, as this long and turbulent chapter draws to a close, the scene is set. The early Earth, now larger and richer in iron from Theia's core, begins its long, slow cooling. Its surface slowly solidifies from a global ocean of magma into a black, crustal scum. It now has a companion, a moon, that loomed much closer in the sky, its immense gravitational pull stirring the molten interior of the young planet. The Cosmic Cradle has delivered its child, a world of fire and rock, poised at the edge of a new chapter, waits patiently in the silent cold of space for the next miracle to occur. Chapter 2: The Cooling World, From Fire to Water. In our last chapter, we left the Earth as a world of fire, a glowing sphere of molten rock, fresh from the cosmic collision that gave it a moon. The violence of its birth was over, but the planet was still a seething, hostile place. Now, we will witness its great transformation. This is the story of how the fiery Earth began to cool, how it built its first skin, how it learned to breathe, and most importantly, how it became a world of water. Let us picture this newborn Earth. Its surface is not solid. It is a global ocean, but not of water. It is an ocean of magma, liquid rock, glowing with intense heat, temperatures soaring over 1,200 degrees Celsius. The entire planet is a ball of fire, with volcanoes erupting constantly, not as isolated mountains, but as vast cracks and fountains across the entire surface. The sky above this magma sea is black, filled with the swirling dust and gas of the young solar system. The first task for this young world was to cool down. But cooling a planet is not a fast process. It takes millions of years. The heat had to escape. This heat came from two main sources. First, there was the leftover heat from the planet's violent formation, the energy from all the asteroid and planetesimal impacts that had built it. Second, and just as important, was heat from deep within the Earth, generated by the decay of radioactive elements like uranium and potassium. These elements are unstable, and as they slowly break down over billions of years, they release energy. This radioactive decay acts like a built-in furnace deep in the planet's core. So how does a planet lose this immense heat? It radiates it out into space. Slowly, over millennia, the surface of the magma ocean began to lose its heat to the freezing vacuum around it, and as it cooled, it began to solidify. Imagine a pot of molten wax. When you turn off the heat, a thin skin forms on top. The same thing happened on Earth. The first solid rocks began to form on the surface of the global magma ocean. This was the birth of the very first crust. But this crust was nothing like the stable continents we have today. It was thin, fragile, and incredibly unstable. Beneath it, the Earth's interior remained molten and churning. Frequently, this hot material from below would break through the thin, solid skin, melting it again and spewing fresh, molten rock onto the surface. The planet was constantly remaking itself, destroying its own skin and creating a new one. It was a dynamic, violent process of creation and destruction. This process of the hot interior breaking through the crust had another crucial effect. It released gases that had been trapped inside the planet. This is called outgassing. Just like opening a warm bottle of soda releases bubbles of carbon dioxide, the churning and erupting Earth released gases from its interior. These gases rose and gathered around the planet, forming Earth's very first atmosphere. What was this first atmosphere like? It was completely different from the air we breathe today. There was no oxygen. It was a thick, toxic soup of gases that would be deadly to us. It was made mostly of water vapor, with significant amounts of carbon dioxide and smaller amounts of nitrogen, methane, ammonia, and sulfur dioxide. This thick, cloudy atmosphere created a powerful greenhouse effect. It acted like a blanket, trapping the heat from the sun and the heat from the planet itself, helping to keep the surface warm even as the young sun was about 30% dimmer than it is today. Now we come to one of the most beautiful and fundamental questions about our planet. Where did the water come from? For a long time, This puzzled scientists. The early inner solar system was a hot, dry place. Any water ice that was near the forming Earth would have vaporized and been blown away by the solar wind. So how did we end up with vast, deep oceans covering 70% of the planet's surface? The answer is that the water was delivered to Earth from space after the planet had formed and begun to cool. It was a gift from the cosmos. There were two main delivery services: comets and asteroids. First, let's talk about comets. Comets are often called dirty snowballs. They are lumps of rock and dust held together by ices, not just water ice, but also frozen gases like carbon dioxide, ammonia, and methane. Comets formed in the outer, colder reaches of the solar system, beyond the orbit of Jupiter. As the giant planets like Jupiter and Saturn settled into their orbits, their immense gravity acted like a gravitational slingshot, flinging millions of comets inward toward the Sun. Many of these comets crossed the path of the inner planets, including Earth. The second delivery service was a special type of asteroid called carbonaceous chondrites. These are very primitive asteroids, some of the oldest objects in the solar system. They are like cosmic time capsules. Unlike the dry, rocky asteroids common in the inner asteroid belt, carbonaceous chondrites are rich in carbon, and, crucially, they contain water, not in the form of free-flowing liquid, but locked within their minerals in the form of hydrated silicates, minerals that have water as part of their crystal structure. For tens of millions of years, the early Earth was bombarded by a gentle, persistent rain of these comets and water-rich asteroids. Each impact was a dramatic event. A comet or asteroid, sometimes miles across, would slam into the Earth's surface at tens of thousands of miles per hour. The immense energy of the impact would instantly vaporize the object, releasing all of its stored water and gases into the atmosphere as a giant plume of steam. This steam would rise into the sky, condense into clouds, and then fall back to the surface as rain. But there was a problem. The Earth's surface was still incredibly hot. So, when this rain fell, it couldn't pool as liquid. It would simply hit the hot rock and sizzle right back into steam, rising back into the atmosphere to begin the cycle again. For a very long time, Earth was trapped in a planet-wide steam bath, with water endlessly cycling between the atmosphere and the hot surface, never able to settle. But the Earth was still cooling. The crust was thickening, becoming more stable. The frequency of massive impacts was decreasing. Slowly, imperceptibly, the surface temperature began to drop. It passed the critical point of 100 degrees Celsius, the boiling point of water. And then it happened. The moment the surface cooled enough, the steam in the atmosphere could finally condense and stay as liquid. The first true rains began to fall, and they did not stop. This was not a gentle shower, but a global, torrential, millennia-long downpour. It was the first rainfall in Earth's history, and it was a deluge of biblical proportions. The water collected in the low-lying basins and depressions on the new, solid crust. It filled the cracks and the craters left by the asteroid impacts. Slowly, over thousands of years, these pools connected, growing larger and larger, until they formed the first primitive oceans. So, by the end of this monumental chapter, the face of the Earth has been utterly remade. The glowing red ball of magma is gone. In its place is a world with a dark volcanic crust. It is wrapped in a thick, cloudy atmosphere of water vapor, carbon dioxide, and nitrogen. And covering most of its surface are the first warm, shallow, global oceans. The world is still a hostile place, with a toxic sky and no breathable air. But the most essential ingredient for the next great adventure has arrived. The stage is now set. The planet has water, and in that water, the next great revolution is. Chapter 3: The Dawn of Life and the Great Transformation. Now, we arrive at one of the most quiet and yet most profound chapters in our story. The Earth, for billions of years, has been a world of physics and chemistry, a world of shifting continents, of erupting volcanoes, of vast, warm oceans under a hazy sky. It is a beautiful planet, but it is a silent one. In this chapter, that silence will be broken, not by a sound, but by a change, a chemical change. This is the chapter where the inanimate world becomes animate. This is the story of the dawn of life. To understand this great mystery, we must first look at the ingredients. The early Earth's oceans were a rich soup, a primordial broth. Within this water were dissolved all the essential elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are the building blocks of all living things. They were stirred by the waves, energized by the sun's ultraviolet light, and by the heat from underwater volcanoes. All the pieces were there, floating in the sea. The great question is, how did they assemble themselves? Scientists have several ideas about where this assembly might have happened. One of the most compelling places is deep at the bottom of the ocean, at a feature called a hydrothermal vent. These are not like volcanoes on land. They are cracks in the Earth's crust on the sea floor, where superheated water, rich in minerals, gushes out into the cold, dark depths. The minerals in this water, like iron and sulfur, can act as catalysts, helping chemical reactions to occur. The vent provides energy, not from the sun, but from the heat of the Earth itself. In this dark, hot, chemical-rich environment, the journey toward life could have begun. Another possibility is that the first building blocks formed in the shallow waters, or even in the atmosphere. Experiments have shown that lightning strikes, or the energy from the sun's rays, could have zapped the simple gases in the early air, causing them to form more complex organic molecules, like amino acids. These molecules, the very ones that make up our proteins, could have then rained down into the oceans, concentrating in tidal pools along the shores. We may never know the exact location or the exact recipe. The process was undoubtedly slow, taking millions, perhaps hundreds of millions of years. It was a patient chemistry happening across the entire planet. But at some point, a threshold was crossed. From this simmering broth of chemicals, a special molecule emerged, or perhaps a system of molecules. This molecule had a remarkable, unprecedented property. It had the ability to make a copy of itself. This was not life as we think of it. It had no cells, no will, no movement. It was simply a self-replicating molecule. Think of it as a template. When the right chemicals floated by, they would stick to this template in a specific pattern and then peel away as a new, identical template. This was the first spark of information, the first instance of something in the non-living world saying, in a chemical language, "Make more of me." This was the foundation upon which everything else would be built. From these first, simple replicators, the next great step was the formation of a cell. Imagine a tiny bubble, a lipid membrane, forming around one of these self-replicating molecules. This bubble acted as a protective barrier. It separated the inner chemistry from the outer chaos. It created a distinct environment, a tiny world within a world. This was the first prokaryote, the first true life on Earth. These first organisms were incredibly simple. They were just microscopic bags of fluid containing their genetic material and the machinery to copy it. They had no nucleus, no internal organs. They were like tiny living chemical factories. To get energy, they simply absorbed the organic molecules that were floating around them in the sea, breaking them down for fuel. This process is called chemosynthesis. For a very long time, this was the only way of life. And then, a revolution occurred, a quiet biological revolution that would change the planet forever. A tiny, simple cell developed a new piece of chemical machinery. It found a way to capture energy directly from sunlight. This process is called photosynthesis. The earliest versions were simple and didn't produce oxygen. They used the sun's energy, but they relied on other chemicals like hydrogen sulfide in their reactions. It was an efficient new way to live. But then, a group of microbes known as cyanobacteria perfected this process. They discovered a new recipe, a powerful new formula. They learned to use sunlight to split water molecules. They took water and carbon dioxide, and with the power of the sun, they created their own food in the form of sugars. And in doing so, they released a waste product that was new to the planet. That waste product was oxygen. At first, this oxygen was not a problem. The early Earth was a chemically reducing place, meaning it was full of elements that were eager to react with oxygen. The most abundant of these was iron, which was dissolved in the oceans. So, as the cyanobacteria pumped oxygen into the water, it immediately reacted with the dissolved iron, causing it to rust. This rust, iron oxide, is insoluble in water. It formed tiny particles that slowly drifted down through the ocean depths, settling layer by layer on the sea floor. Over millions of years, these layers built up, creating vast, striped rock formations that we call banded iron formations. These beautiful, rust-colored bands in ancient rock are the direct evidence of this great oxidation event. They are the geological record of the Earth slowly rusting. For hundreds of millions of years, this process continued. The cyanobacteria produced oxygen, and the oceans soaked it up by rusting. But eventually, a saturation point was reached. The oceans ran out of free iron to rust, and so oxygen, this new reactive gas, began to leak out of the oceans and into the atmosphere. For most of the life on Earth at that time, this was a catastrophe. They had evolved in a world without oxygen. To them, oxygen was a deadly poison, a corrosive gas that destroyed their delicate chemistries. This first global pollution event, caused by the success of the cyanobacteria, likely triggered a mass extinction. Countless species of ancient microbes, unable to protect themselves, vanished forever. But in evolution, a crisis for some is an opportunity for others. In the midst of this oxygen crisis, some organisms did not just learn to tolerate the poison, they learned to use it. They developed a new, vastly more efficient way to breathe. This process is called aerobic respiration. It involves using oxygen to break down food molecules. The amount of energy that can be released from a single sugar molecule using oxygen is nearly 20 times greater than without it. This was a quantum leap in energy production. It was like upgrading from a simple campfire to a powerful engine. This new, abundant energy source was the key that would unlock the door to more complex life. The final major innovation in this chapter was the rise of the complex cell, the eukaryote. All the life we have talked about so far, the bacteria, the archaea, are prokaryotes, simple cells without a nucleus. But then, a new type of cell appeared, with a central command center, the nucleus, to house its genetic material. It also had other specialized structures inside, called organelles. And the story of how this happened is one of the most beautiful in all of biology. It is the theory of endosymbiosis. The word means living together inside. The idea is that one day, a large prokaryote swallowed a smaller oxygen-breathing bacterium. Instead of digesting it, a truce was called. The small bacterium continued to live inside the large one. It was safe, and it had a steady supply of food. In return, it used its amazing ability to perform aerobic respiration, providing its host with a generous supply of energy. This partnership was so successful that the two became inseparable. The smaller bacterium evolved into what we now call the mitochondria, the powerhouse of the cell. Later, a similar event occurred. A eukaryotic cell swallowed a cyanobacterium, and again, instead of being digested, the cyanobacterium stayed. It provided its host with food through photosynthesis. It evolved into the chloroplast, the organelle that allows plants to make their own food from sunlight. This was not a battle, but a merger. Life learned to build complexity, not just through competition, but through cooperation, through collaboration. So, as this long chapter draws to a close, the Earth is a transformed world. The atmosphere, once thick with methane and carbon dioxide, is now filling with oxygen. The oceans, once ruled by simple microbes, are now shared with much larger, more complex eukaryotic cells. These new cells, with their internal power plants and specialized compartments, hold within them the potential for truly magnificent things. The quiet, chemical planet has found a new biological rhythm. The stage is now set for life to grow large, to grow complex, and to truly begin its grand evolutionary dance. Chapter 4: the long dance of the continents, and the rise of animals. In our last chapter, life was a quiet, microscopic world, thriving in the oceans. The air was becoming rich with oxygen, thanks to the work of countless cyanobacteria. Now we will witness how the planet itself began to move in a slow, grand ballet, and how this physical dance set the stage for life to explode in size, complexity, and wonder. This is a story of two interconnected revolutions, one of the Earth's body and one of its living inhabitants. First, we must understand the powerful, slow-moving engine that drives the planet's transformation: plate tectonics. The Earth's outer shell, called the lithosphere, is not a single, unbroken eggshell. Instead, it's broken into huge, interlocking plates, like a giant, rocky jigsaw puzzle floating on the hot, soft, and malleable layer of rock beneath them, the asthenosphere. These plates move incredibly slowly, about the same speed your fingernails grow, just a few centimeters per year. They drift apart, they collide, and they slide past one another. This process, so gradual we cannot feel it, is the most important force in shaping the face of our planet over billions of years. This constant movement means the map of our world has never been permanent. The continents we know today are just a single frame in a film that has been playing for billions of years. Throughout Earth's history, they have repeatedly crashed together in a slow-motion embrace, forming giant supercontinents, only to later tear themselves apart again. Long before the famous Pangaea, there were others with names like Rodinia and Nuna. Imagine a world with just one massive landmass, a single colossal continent surrounded by a global ocean. Then, over hundreds of millions of years, forces deep within the Earth would slowly, inexorably, rip that supercontinent apart. Its pieces would drift across the globe like giant, rocky rafts, carried by the convecting currents in the mantle below, only to eventually collide again and form a new supercontinent in a completely different configuration. This cycle of assembly and breakup has happened again and again, sculpting the planet's surface, driving the evolution of climate, and profoundly influencing the story of life. Now, let's return to the story of life in the oceans. For over 2 billion years, it remained mostly microscopic, but the rise of complex eukaryotic cells, with their powerful mitochondria providing abundant energy, set the stage for a new breakthrough: multicellularity. This is the revolutionary idea that individual cells could specialize, coming together to work as a single, larger organism. It was a new form of biological cooperation. One cell could specialize in digestion, another in providing structure, another in sensing the environment, and another in reproduction. This division of labor allowed for efficiencies and complexities that were impossible for a single solitary cell. The first tentative experiments in this new way of life appear in the fossil record about 600 million years ago, in a period we call the Ediacaran. The creatures of this time were truly strange and alien, unlike anything we see today. They were soft-bodied, leaving only faint impressions in the mud that turned to stone. Some were shaped like discs, others like fronds or segmented carpets. They had no heads, no mouths, no legs, and no guts. Scientists believe they likely sat stationary on the seafloor, absorbing nutrients directly from the water through their skin. They were a quiet, gentle, and ultimately fragile experiment in being a large, complex organism. For millions of years, these were the most complex forms of life on the planet, a world of peaceful, strange beings in the deep. Then, around 541 million years ago, something remarkable happened. In a geologically short period of about 20 to 25 million years, the ocean suddenly teemed with an explosion of new life forms. This event is called the Cambrian explosion. It was as if life, after 3 billion years of slow, patient experimentation, had suddenly discovered a whole new toolkit of biological blueprints. The game of life changed forever. For the first time, the fossil record is filled with creatures that had hard parts: shells, spines, claws, and armored plates. This is one reason we know so much about them. These hard parts fossilize beautifully. This is when the major groups of animals, or phyla, that we know today, first appeared in the fossil record. The rules of the game had changed. Imagine diving into a Cambrian sea. The water would be full of bizarre and wonderful creatures. You might see Opabinia, a strange animal with 5 eyes and a long, flexible nozzle-like appendage with a claw on the end, like a vacuum cleaner from a dream. You would see Anomalocaris, a fearsome predator that grew to over 1 meter long, with grasping appendages in front of its mouth and large, complex eyes, making it the apex predator of its time. Most importantly for our own story, you would see the first primitive chordates, like Pikaia, a small, eel-like creature with a notochord, a flexible rod along its back that is the precursor to a backbone. This humble animal is one of our very distant ancestors. What caused this sudden explosion of diversity and complexity? It was likely a perfect storm of factors, a confluence of environmental and biological triggers. Oxygen levels had finally risen high enough in the atmosphere and oceans to support the high energy demands of larger, more active animals. The evolution of predation, animals eating other animals, created an evolutionary arms race. If you were a prey animal, there was a tremendous advantage to developing a hard shell for defense, or spines to make you harder to eat. If you were a predator, you needed better senses, like eyes to spot your prey, and better mobility to catch it. This competitive pressure drove innovation at a breakneck pace. The evolution of eyes was particularly transformative. For the first time, animals could see their world in detail. They could hunt with precision, avoid predators from a distance, and navigate complex environments. Light became a new medium for information, and the world was no longer a place of simple chemical and tactile senses. It was now a place to be seen. So by the end of this chapter, the Earth is truly, vibrantly alive. Its landmasses continue their constant, slow dance, colliding and tearing apart in a cycle that spans eons. Its oceans, once the quiet home of microbes and simple fronds, are now a bustling, dynamic, and competitive world, filled with a stunning diversity of animal life, from filter feeders to active swimmers, from the heavily armored to the cleverly camouflaged. The quiet, patient planet of microbes has been replaced by a world of action and interaction. The stage is now set for life to make its most audacious move yet, to leave the water, conquer the barren, empty continents, and turn the world green. Chapter 5: The Age of Giants and the Great Resets. In our last chapter, we witnessed life's spectacular explosion in the oceans during the Cambrian period. The seas were filled with strange and wonderful creatures, and the first animals with backbones, our very distant ancestors, had made their appearance. Now we will follow life as it makes its boldest move yet, leaving the water to conquer the land, and witness the rise and fall of the most spectacular creatures to ever walk the earth. This is a story of conquest, of giants, of catastrophe, and of resilience. The continents, for billions of years, had been barren landscapes of rock, battered by wind and rain. There was no soil, no greenery, no sound but the weather. The first pioneers to change this were not animals, but plants. Around 470 million years ago, simple, moss-like organisms began to cling to damp rocks near the water's edge. They were the first invaders of the land. These primitive plants had no roots or vascular systems to transport water. They simply absorbed moisture directly through their surfaces. But they were tough, and they began the slow work of creating soil, breaking down solid rock with acids and their tiny root-like structures. Following these first green pioneers came the animals. The first to venture out of the water were likely relatives of modern scorpions and millipedes. They crawled onto land to feed on the microbial mats and decaying plant matter that now lined the shores, or perhaps to escape predators in the water. They had to evolve new ways to breathe, developing early versions of lungs or book gills to extract oxygen from the air instead of water. They also needed to develop ways to prevent their bodies from drying out in the open air. This was a huge evolutionary hurdle, but the rewards, new food sources and new habitats, were immense. This led to the age of the first great forests during the Devonian and Carboniferous periods. These were not forests of oak and pine, but of strange, giant plants. Towering club mosses, horsetails, and ferns grew to the size of modern trees, creating the first dense, shadowy jungles on Earth. The air was thick with humidity, and the atmosphere was rich in oxygen, reaching levels much higher than today. The swampy lowlands were vast, warm, and teeming with life. In these steamy swamps, life continued its experiments. Fish, which had been evolving in the oceans for millions of years, began to adapt to the shallow, oxygen-poor waters. Some, like the famous Tiktaalik, developed sturdy, lobed fins that could support their weight. These fins had the basic bone structure of a land animal's limb, with a primitive wrist and what would become fingers. Tiktaalik was a true fisherpod, a fish with the head of a crocodile and the shoulders of a land animal. It could likely push itself up in the shallow waters, using its fins to navigate through vegetation and perhaps even spend short periods out of the water. This was a crucial bridge between two worlds. From these early amphibious pioneers arose the reptiles, who developed a revolutionary new technology, the amniotic egg. Unlike the soft, jelly-like eggs of fish and amphibians that had to be laid in water, The amniotic egg was a self-contained life support system. It had a hard or leathery shell to prevent drying out, a yolk to provide food, and a series of membranes that protected the embryo and allowed it to breathe air. This incredible invention was like a private pond for each developing baby. It freed reptiles completely from the water to reproduce, allowing them to conquer the dry interiors of the continents and spread far from the shores. But the story of life on Earth is not one of steady, uninterrupted progress. It is a story punctuated by catastrophe. Around 252 million years ago, at the end of the Permian period, the planet experienced its most severe crisis. The Great Dying Massive, prolonged volcanic eruptions in a region we now call the Siberian Traps, spewed unimaginable amounts of lava, gas, and ash into the atmosphere for nearly 1 million years. This triggered a runaway greenhouse effect, warming the planet, acidifying the oceans, and stripping them of oxygen. It is estimated that over 90% of all marine species and 70% of terrestrial vertebrate species were wiped out. The planet became a stifling, toxic wasteland. It was the closest life has ever come to being completely erased. But from the ashes of this near-total extinction, a new world emerged. In the emptied ecosystems of the following Triassic period, a new group of reptiles began to rise to dominance. The archosaurs, the ruling reptiles. From this group, two famous lineages would evolve: the crocodilians and ultimately the dinosaurs. The dinosaurs were not initially the giants we imagine. They started as small, fast, likely bipedal creatures, scurrying in the shadows. But they possessed a more upright posture and more efficient locomotion than their competitors. As they diversified, they grew in size and variety. By the Jurassic and Cretaceous periods, they had become the most spectacular rulers the planet has ever seen. They were not all giants, and they were not slow and lumbering. Many were agile, fast, and some were feathered. The world was filled with a breathtaking array of forms, from the massive, long-necked sauropods like Argentinosaurus, which shook the ground as they walked, to the highly intelligent and social pack hunters like Velociraptor, to the ultimate predator, Tyrannosaurus Rex. But the dinosaurs did not rule alone. During their reign, two other key evolutionary events were quietly taking place, which would be crucial for the future. The first was the evolution of the first mammals. Appearing in the shadow of the giants, these early mammals were tiny, shrew-like creatures, likely nocturnal. They survived by staying out of sight, feeding on insects and small plants. They had key advantages, however. They were warm-blooded, had fur for insulation, and most importantly, they gave birth to live young, which they nourished with milk, allowing for greater parental care. The second event was the evolution of flowering plants, or angiosperms. Before this, the world was dominated by conifers, ferns, and cycads. The rise of flowers, with their bright colors and sweet nectar, created a new partnership with insects for pollination. This coevolution led to an explosion of new plant and insect diversity, creating the vibrant, colorful ecosystems we would begin to recognize today. The age of dinosaurs came to a sudden, dramatic, and definitive end 66 million years ago. An asteroid perhaps 10 kilometers wide, slammed into what is now the Yucatan Peninsula in Mexico. The impact was apocalyptic. It released energy billions of times greater than a nuclear bomb, triggering mega tsunamis, global firestorms, and ejecting so much dust and sulfur into the atmosphere that it blotted out the sun for years. This impact winter halted photosynthesis, collapsing the food chains both on land and in the sea. The dinosaurs, along with about 75% of all plant and animal species, perished. It was a swift, terrible catastrophe. But in every ending, there is a beginning. The demise of the giant reptiles opened the world for the small, furry, and resilient survivors. With the dinosaurs gone, the age of the mammal had finally arrived. No longer confined to the shadows of the night, these warm-blooded, adaptable creatures would now step into the sunlight and empty landscapes and begin their own incredible journey of diversification. A journey that would, much later, in the blink of a geological eye, lead to us. The world was reset once more, ready for its next great act. Chapter 6: The Age of Mammals, Ice and Consciousness. In our last chapter, we witnessed the dramatic end of the dinosaurs' reign. A fiery impact and a long winter had silenced the world of giants. The great reptiles were gone, and the earth was once again quiet, its forests and plains emptied of their most magnificent creatures. But as we have seen time and again in our planet's story, emptiness is an opportunity. In this chapter, we will watch as the small, surviving creatures step out of the shadows to inherit the earth, and how a new kind of intelligence slowly awakened. The world after the asteroid impact was a damaged one. The climate was unstable and ecosystems were shattered. But the survivors were a tough and adaptable bunch. Among them were the mammals. For over 150 million years, they had lived as small, nocturnal animals, rarely larger than a badger, surviving by hiding in burrows, climbing trees, and feeding on insects and plants under the cover of darkness. Their time had finally come. With the dinosaurs no longer dominating the landscape, mammals began to explore new ways of life. This process is called adaptive radiation. Imagine a vacant lot that slowly gets taken over by all sorts of different plants, each finding its own special spot in the sun. That's what happened to mammals. They diversified into the many empty jobs in nature. Some grew large and evolved to become grazing animals, the ancestors of horses, deer, and elephants. Others became predators, evolving into the first cats, dogs, and bears. Some returned to the water, their bodies slowly transforming over millions of years into the streamlined forms of whales and dolphins. Others took to the air, developing flaps of skin to become bats. The continents, still slowly drifting, carried these evolving lineages to all corners of the globe, leading to the unique wildlife we see in Australia, South America, and Africa today. A key event in our own story happened during this time, around 60 million years ago. A small, unassuming group of tree-dwelling mammals evolved. The primates. Life in the trees was a training ground for the traits that would one day define us. They developed forward-facing eyes for judging distances as they leaped from branch to branch, giving them depth perception. They evolved nimble fingers with opposable thumbs for grasping branches, fruit, and insects. Their brains, needed for the complex task of navigating a three-dimensional forest world, grew larger in relation to their body size. This was the humble beginning of our own family tree. Then, the planet's climate began to shift in a profound way. The world, which had been a warm greenhouse planet for so long, started to cool. The driver of this change was a slow geological process, the carbon cycle. The formation of massive mountain ranges like the Himalayas and the Andes exposed fresh rock to the air. This rock chemically reacted with carbon dioxide in the atmosphere, slowly drawing it down and locking it away. With less of this greenhouse gas to trap the sun's heat, the planet's thermostat began to turn down. This cooling trend culminated in the last 2.5 million years in a series of ice ages known collectively as the Pleistocene epoch. This was not one long, unbroken freeze, but a roller coaster of glacial cycles. For about 100,000 years at a time, vast ice sheets, often over a mile thick, would slowly creep down from the poles, covering much of North America, Europe, and Asia. These were landscapes of breathtaking scale and silence, of white and blue ice under a pale sun. So much water was locked up in these ice sheets that global sea levels dropped by over 100 meters, exposing land bridges that connected continents. Asia was connected to North America via the Bering Land Bridge, and you could walk from Britain to France. Then, the cycle would turn. A warmer interglacial period would arrive, lasting about 10,000 to 15,000 years. The ice would retreat, the sea levels would rise, and the land would bloom again. We are living in one of these warm, interglacial periods right now, called the Holocene. This unstable, unpredictable world of shifting climates was a crucible for evolution. It was during these turbulent cycles that our own lineage, the hominins, walked onto the stage in Africa. The story of human evolution is not a simple ladder leading directly to us. It is a rich branching bush with many species existing, adapting, and going extinct over millions of years. What set our ancestors apart was a suite of adaptations that together proved to be powerful. The first was walking upright, or bipedalism. This freed the hands from the task of locomotion. Now, hands could be used to carry food, to manipulate objects, and eventually to make tools. Then, their brains began to grow in size and complexity. They learned to chip stones into consistent, sharp-edged tools, a technology that remained largely unchanged for 1,000,000 years. The control of fire was a revolutionary leap. It provided warmth, allowing our ancestors to spread into colder climates. It offered protection from predators, and crucially, it allowed for cooking. Cooked food is easier to digest and provides more energy, which may have provided the extra fuel needed to power those larger, more energy-demanding brains. The most recent of these hominins was Homo sapiens. What we lacked in physical strength, we made up for with an unprecedented intelligence and a capacity for symbolic thought and complex language. Language allowed for the sharing of complex ideas, for coordinated hunting, and for the accumulation of knowledge across generations. With these skills, we spread out of Africa around 60,000 to 70,000 years ago. We were a truly global species, navigating the changed world of the Ice Age, using our wits to survive in environments from the steppes of Asia to the frozen tundra of Europe, eventually reaching every continent on Earth except Antarctica. Our arrival often coincided with the extinction of the great megafauna, the woolly mammoths, the giant ground sloths, the saber-toothed cats. Whether through overhunting, the spread of disease, or the habitat changes we brought, our species became a new, powerful geological force. The final great transition happened only about 10,000 years ago, as the last ice age retreated. In various parts of the world, from the Middle East to China to the Americas, groups of humans began to shift from a nomadic life of hunting and gathering to a settled life of agriculture. They domesticated plants like wheat, rice, and corn, and animals like goats, sheep, and cattle. This was the Neolithic Revolution. It allowed for permanent settlements, the accumulation of resources, and a population boom. Villages became towns, towns became cities. With agriculture came writing, invented to keep records of crops and trade, and history, as we commonly define it, began. And so we arrive at the present moment, a species that can look back and tell this 4.5 billion year story, a species that can study the stars from which we came and the planet that forged us. We are the universe, become aware of itself. Our story is now intertwined with the planet's in a way no other species has ever been. We have become the stewards of its future, for better or for worse. The long, patient journey from a cloud of dust to a living, thinking world is complete. The story continues with us. Conclusion: the pale blue dot, aware of itself. And so, we have reached the end of our journey. We have traveled across an almost unimaginable span of time, 4.5 billion years. We began in a silent cloud of stardust, and we have arrived here, now, on a world teeming with life, sound, and thought. Let us take a final, quiet moment to look back at the path we have walked. We witnessed the gentle chaos of the solar system's birth, the patient gathering of stardust into planets. We saw our own Earth, born in a fiery collision, gifted with a moon that would become its eternal companion. We watched as it cooled, its surface solidifying from a global ocean of magma into a black crust, while a toxic atmosphere slowly gathered. Then came the water, delivered on the backs of comets and asteroids, falling as a rain that lasted for millennia, until the first shallow, warm oceans formed. And in those oceans, in the deep darkness near hydrothermal vents or in the sunlit shallows, a miracle occurred. A chemical whisper, a molecule that could copy itself, broke the silence of the cosmos. Life had begun. It was a patient, microscopic world for billions of years, until a new kind of cell, the eukaryote, learned the power of cooperation, incorporating other cells to become complex, energy-rich beings. Then, in a breathtaking explosion of form and function, animals appeared, filling the seas with movement and purpose. Life, once confined to the water, then dared to venture onto the barren land, first with plants that created soil, then with animals that learned to breathe air. we saw the great dynasties rise and fall, the age of giant amphibians in steamy coal swamps, the rise of reptiles and their revolutionary amniotic egg, and the terrible near-total reset of the Great Dying. From that devastation, the dinosaurs emerged, ruling the planet for an astonishing 150 million years, a world of giants we can only try to imagine. And we witnessed their sudden, dramatic end, a chance impact from space that cleared the stage for the small, furry, warm-blooded survivors, the mammals. In the age of mammals, our own lineage took shape in the trees, developing the keen senses and nimble hands that would one day prove so crucial. The planet itself then entered its great ice age cycles, a world of advancing and retreating glaciers that tested the adaptability of all life. And in that crucible of change, one particular lineage of mammals stood upright, freed its hands, harnessed fire, and began to shape the world with tools and eventually with words. This entire story, from the first dust grain to the first human thought, is a story of one thing above all else: change. The Earth is not a static museum piece. It is a dynamic, ever-evolving system. Its climate has swung from hothouse to icehouse and back again. Its life has faced 5 major extinctions, each one a devastating ending that, in time, forged a new and often more complex beginning. The story of Earth is a testament to resilience, to life's incredible tenacity and its boundless capacity for adaptation. And now, here we are, Homo sapiens, a species that can look back and tell this story, a species that can decipher the clues left in rocks, in ice, and in our own DNA. We are the product of every chapter that came before. The iron in our blood was forged in the heart of a dying star billions of years ago. The air we breathe was gifted to us by trillions of ancient cyanobacteria. The water we drink fell from the sky during the planet's first great rains. The very structure of our bodies, with its complex cells and powerful mitochondria, is the result of an ancient cooperative merger. We are not just on the Earth, we are of the Earth. We are the universe, become conscious of itself. We are a way for the cosmos to look back upon itself and know its own history. When the Voyager 1 spacecraft turned its camera back towards home from the edge of our solar system, it captured an image of Earth as a tiny, pale blue pixel, suspended in a sunbeam. That pale blue dot, as Carl Sagan called it, is everything we have ever known. Every king and queen, every hero and coward, every creator and destroyer, every joy and every sorrow, all of it contained on that single, fragile speck of dust. As you rest now, let the vast, deep time of Earth's history settle over you like a gentle blanket. Let the sheer scale of this story quiet the noise of the day. The struggles and worries of this moment are real, but they are also a single, fleeting frame in a film that has been playing for 4.5 billion years. You are part of this grand, beautiful, and ongoing story. You are connected to the stars, to the first life in the ancient seas, to the giants who walked the land, and to the countless generations of ancestors who adapted, survived, and passed their spark on until it finally, miraculously, reached you. So, rest. The story is not over. It continues with us. with every breath we take and with every thoughtful action we make. The long journey from stardust to consciousness is complete, but the next chapter is still being written. Good night.